The subject of this abstract is diffusion-weighted MR spectroscopic imaging at 7T, using a single-shot diffusion trace-weighted sequence with tetrahedral gradient encoding. Diffusion-weighted MRS at 7T provides a capability of mapping the diffusion coefficient across multiple voxels within a volume of interest. The diffusion coefficient can provide information about the underlying intracellular environment underlying various pathologies. The imaging is achieved with radial echo-planar trajectories using symmetric bipolar gradients. This allows for an acceleration of the imaging time relative to conventional MRSI. It also allows for achieving a reduced field of view acquisition from an undersampled set of spokes. And importantly, it provides a capability for self-navigation, which is important for doing corrections on the data. Another important feature of symmetric echo-planar spectroscopic imaging is that the even and odd echoes can be separated in order to achieve the larger spectral width, which is important for 7T. This sequence is mapping the trace apparent diffusion coefficient, which is the sum of the diagonal of the diffusion tensor, which reflects an average mean displacement per unit time of any diffusion molecules within the measured volume. This trace apparent diffusion coefficient depends on the diffusion direction and the scaling of the gradients that are applied along all gradient axes. Importantly, it is also dependent upon the diffusion time, which is the amount of time during which the molecules are allowed to diffuse before completing the measurement. The sequence considered in this abstract is a single-shot sequence in the sense that it produces within 1 TR a diffusion weighting that is reflecting the trace of the diffusion tensor, whereas conventional pulses require 3 separate measurements along orthogonal diffusion directions to achieve the trace ADC weighting. The goal of this abstract is to show preliminary results of this single-shot sequence at 7T using radial echo-planar spectroscopic imaging and semi-laser localization in phantom and in vivo. 3 data sets were measured in phantom and 2 from healthy volunteers using a Siemens Terra 7T scanner. The field of view was 320 by 320 millimeters with a slice thickness of 15 millimeters and a measure size of 32 by 32, which translates into an in-plane resolution of 1 centimeter and 1 centimeter. 33 radial spokes were acquired as opposed to a fully sampled 50, and the even and odd echoes were reconstructed separately in order to achieve a spectral width of 2,380 Hz with 1,204 time points. The tetrahedral encoding scheme shown in this slide allows for the measurement of a signal that is weighted by the trace of the ADC. The diffusion gradient parameters considered here allowed for 2 b-values in phantom and in vivo. In phantom, b-values range from 3 to 1,527 seconds per millimeter squared, whereas in vivo, the b-values measured were 53 and 1,670 seconds per millimeter squared. Importantly, the diffusion time is 30.8. Gradient delay and EPI phase corrections were applied, and the navigator echoes were used in order to phase the spectra that is affected by diffusion during the measurement time. And all radial data were reconstructed with NUFFT-based reconstruction. For the phantom data, the mean phantom ADCs were determined within 5 subregions of the VOI, which contained a 10 by 10 matrix. This was done to determine the homogeneity of the ADC values and to compare with reference values for this particular phantom. All data was quantified with LC model, and metabolite estimates with CRLBs of less than 30% were considered in the ADC calculations. This table shows the ADCs of 6 metabolites within the phantom, GE Brano phantom, and these were averaged across 5 different regions, subregions shown above, ranging from a 2 by 2 matrix to a 10 by 10. The results show that the ADCs measured corresponded well with the reference ADCs previously published, shown on the right column. These are metabolite maps from the 6 metabolites contained within the phantom. Some inhomogeneity is experienced in these metabolite maps due to B0 and B1 inhomogeneity, and due to the fact that the RF pulses are not optimized for this particular application. These are examples of in vivo maps, which again show some inhomogeneity due to the suboptimal RF pulses being played. In the lower part of the figure, you see histogram values, which show a relatively wide spread of the values, although these are not too far off from previously reported values in human. These are examples of diffusion-weighted spectra and non-diffusion weighted spectra in vivo within the volume of interest. Red has been diffusion weighted by a b-value of approximately 1,670, whereas the blue is the non-diffusion weighted b-value, or at a low b-value of 53 seconds per millimeter squared. In general, this was a preliminary pilot study, but results show that phantom ADCs were approximating the range of values previously reported from reference values, except for certain metabolites such as lactate and glutamate, which were overly estimated. In vivo, only 3 main metabolite groups were able to be reliably estimated with CRLBs less than 30%. These are total creatine, total NEA, and total choline. Unfortunately, glutamate was not able to be quantified very reliably. Possibly due to the relatively short diffusion time of 30.8 milliseconds, the ADCs are slightly higher than those determined previously, although these results are affected by the fact that the VOI was not selected in an optimal way. Preliminary results show good agreement in the estimated phantom values, while the in vivo trace ADCs are generally within the expected range of those reported in vivo, although these tend to be higher than previously reported. This could be due to the suboptimal adiabatic RF pulses that have been played to localize the volume of interest with this semi-laser based sequence. The limitations of this radial echo-planar spectroscopic imaging when it comes to diffusion weighting is that it requires a long TE, higher gradient amplitudes to reach the necessary B values, and increased B1 and B0 inhomogeneity and chemical shift displacement artifacts, which are higher at 7T. Further optimization is needed to optimize this particular methodology. Acknowledgements are given to the Laboratory of Neuroimaging at USC and the USC Laboratory of Functional MRI Technology. Thank you.